Okay, so we're going to switch gears. We're going to start talking about serviceability level loads, and we're going to start talking about fire. This project, the WOODWISE project, is a collaboration between Oregon State University, the EPA, and the Forest Products Lab. We've been working on this project for probably about 6 years, kind of all the way from the figuring out what we wanted to test through getting funding and then doing our compartment fire burns last year. So the goal of this is that there has been a lot of compartment fire tests. I'm going to be adding to the data, but there has been a lot of compartment fire tests throughout the world. And I'm showing you all of them here. And this is, what the fuel load was, what the percent exposed mass timber was. But in a lot of these tests, they're using pretty low fuel loads. And they're also using wood cribs or kerosene pools that are as the fuel itself. And so if we look around this room, I don't see any wood cribs and I don't see any kerosene pools. And if we think about what's in our homes, what's in our offices, right? The modern furniture that we have has a lot of synthetics. Cellulose-based fuels are not going to be representative of modern fuels. And so our goal with this project is to really test at high fuel loads and to test real furniture and explore how that changes maybe the fire dynamics in the space and what we can learn from that. And so if we take that crazy chart and data that I just showed you and make it a little bit more digestible, and see that at these high fuel loads, there aren't a lot of tests. And every single one of these tests used wood cribs, or they used something that was not representative of actual fuels. And so what we did is we tested 3 compartments over 4 tests. The way that we were able to do that is test 1 and test 4 were fully encapsulated, so the timber was not damaged and we could rip it all out and test again. You can see the dimensions of the test here, but most importantly, in the middle of the compartment, there was a glulam beam column frame, and that's going to come up a little bit later. All of these tests were performed at the Alcohol, Tobacco, and Firearms Laboratory in around Washington, D.C. The CLT was Southern Yellow Pine. All of the CLT was 5-ply, except for the floors were 3-ply with 2 layers of concrete cement board on top of it. So we didn't want the floors to fail. The floors then also span between these stringers, and that allowed us to move the compartments around. So we really want to look at fire performance of these compartments. So fire performance of the mass timber. We wanted to look at the structural and serviceability performance. So how did that perform structurally? And then lastly, we are partnering with the EPA. So we wanted to look at how emissions changed throughout these tests. How do the emissions change if we are encapsulating the timber versus not encapsulating the timber? So we addressed a lot of the gaps in knowledge, and we spent a few years actually identifying these gaps in knowledge and strategically deciding what would be beneficial to add to the body of work that's already out there. And we knew it was going to be high fuel loads, fuel that contained furniture, and tests that were allowed to enter the decay phase. So oftentimes tests are put out prior to them entering that decay phase. What these looked like inside, this was test number 1. For those that are attached to Squishmallows, that was probably the most contentious part of our test. Most commented part about it on Instagram and on LinkedIn. But this is what the back of the compartment looked like. And so this is what it looked like with wood cribs. So test number 1 and test number 4 were exactly the same, except one used wood cribs and one used furniture. So that allowed us to actually compare the difference in the fire demand in the space, temperature, heat flux, time, etc. Test number 2 was fully exposed. There was no encapsulation in the compartment. And test number 3 only had encapsulation on the longitudinal walls. So on the long walls, there was encapsulation, but the ceiling was left exposed. And so there is an insane amount of data on these tests. I could stand here for hours. So I'm only going to talk about some char rates that we've calculated. Okay, so char rates in test number 2 and test number 3. So some of our instrumentation, we had what we call thermocouple trees, and we had these laid out throughout the entire compartment. This allows us to measure gas temperature throughout the entire compartment. The red dots are the locations of those. This is a plan view. And what this looks like in elevation is here. So we have thermocouples from floor to ceiling at about 15 inches, 15.5 inches, all the way up. So we can actually then calculate time to flashover, and we can look at when the temperatures are uniform from floor to ceiling. It also allows us to look at how the fire moved throughout the space. We then were also calculating char rates in the CLT. So the blue stars are where we had embedded thermocouples in the walls. We also had tons of surface thermocouples, and the green stars are where we had embedded thermocouples in the ceiling. And I realized everything here is in millimeters, but you kind of get the gist of how these all were embedded into the CLT. So we can calculate char rates based on when these thermocouples reach 300 degrees Celsius. At that time, we just take the time divided by the distance that these thermocouples are, and we have a char rate. Timber chars at 300 degrees Celsius. Okay, so let's talk about some results. So if we look at test number 2 with no encapsulation at all, we can see that the left wall and the right wall behave very similarly. In the front of the compartment, we have about similar char rate for the ceiling, but in the back of the compartment, that char rate is a bit elevated in the ceiling. If we begin to compare this against what is suggested by NDS, we might see that this is quite different, especially in the front of the compartment, right? All of these standard prescriptive char rates are determined using a standard fire, but we're putting them in our buildings, and these are natural fires that occur in our buildings. So we're seeing a vast difference in the char rates from that standard to natural fire. If we look at just the ceiling char rates, we begin to see some differential between test number 2 and test number 3, where test number 3 was partially encapsulated. So we actually saw that in test number 3, we had faster time to flashover. We also saw higher temperatures, although we saw a little bit lower maximum heat release rate. So a little bit less intense fire, higher temperatures though. And so we're seeing, the result of that in the char rates in the ceiling itself. And these are average linear char rates over all of those thermocouples. We have individual results. It just takes a little bit of time to go through. But again, comparing this with NDS, right, we can see large differentials here between what we're measuring in the experiment and what we're seeing in our codes, right? So just some conclusions on the char rates, and we have tons of data on this. We're seeing faster char rates in the front of the compartment, higher variability with char rates in the back of the compartment. We're seeing that we actually saw a more intense fire when we had partial encapsulation than we had fully exposed compartments. And almost all the char rates were greater than the prescribed char rates in our codes. Okay, so other things we are doing is comparing temperatures throughout the compartment, back and front. We're examining emissions data from the fires themselves. So developing suggestions for charring on vertical versus horizontal surfaces. And we had actually some balloon frame construction connections in the back of the compartment, and we're doing investigations on screw hinging and balloon frame construction connections in fire. This project is also funded by the EPA and NEFA. So this is, a multi-funder project. And there were a lot of organizations that helped us. Many of you are in the room, put these on, and here's a website for the project itself if you want to check out some updates. Okay, we're almost there, I promise. So, all of us have been talking about a lot of research results, and I know like the whole purpose of this symposium is to really put out and share all these research results with you. But one of the greatest results coming out of all of these projects are our students. And these are all the students that I've had that have worked on TDI funded projects. These are not all the students I've had, but just the TDI funded project ones. And there's a lot of students going out and working with all of you. And so I do want to just thank you all for sitting on our advisory committees and answering our questions and donating material and supporting our research, because this is the real outcome that comes out of this, and they can come out and work with all of you. Okay, so still not done. So some exciting news that Ian mentioned at the beginning. We have something very exciting coming to OSU. We have a fire lab. We will be breaking ground in December. The building will hopefully be built by 2027 and be operational in 2028. This will be right next door to Emerson. So when we head over there, yeah, it's very, very exciting. So when you head over there, in a few years, there won't be just this empty side to Emerson. We'll have another building there, and you'll be able to tour that as well. And so we're really kind of adding on to the capacity of testing at Oregon State University. We'll be able to do wall and floor testing and connection testing in a tilt furnace and a gas-fired furnace. As Ian mentioned, it's about to set sail on the open seas. We will have an open burn area that's about 1,200 square feet where we can conduct about a 3 megawatt fire, which is about the size of a 12 by 12 garden shed or a car. We'll have a calorimetry hood that we'll be able to collect emissions data with, as well as characterize the fire intensity, and a crane. It was kind of a big deal to get the crane, so I have to mention that. And there's a lot of capabilities that we have there, right? So we will be able to do testing on everything that I'm showing you here on the screen. It's not just for mass timber testing, but in fire testing, but we have huge gaps in knowledge on the behavior of our structures and our infrastructure in wildfires. Being able to test structural steel, we have ceramic fiber heaters that will be able to do that outside of a furnace if need be. And as well as, testing in the furnace itself. We will be able to, examine more about how we can prevent structure-to-structure fire spread in wildfires. As I'm showing on the screen here, this type of testing will be capable in the laboratory, but also examining fuel for cooking stoves in developing countries and making sure that the emissions from these stoves are safe for the people who are operating them. More burning structures. We're actively looking for industry partners on this. So if you are interested in being involved and supporting this work, please let me know. Come talk to me during the happy hour or during our Emerson tour. And as I mentioned before, we are groundbreaking later this year. Maybe we'll have a barbecue. We'll have our structure complete end of 2027 and be ready for testing with you all in 2028. Thank you very much.